Good morning. So in the lectures till now, we have been looking at the measurement of various electrical and non-electrical quantities, and also various instruments that can be used to uh, perform these measurements. However, it is very common knowledge that each and every measurement is subject to error, and error is caused by various sources of uncertainties or lack of complete knowledge of the entire measurement system, or lack of exact knowledge of the complete measurement system. So even though there is uncertainty caused in the measurement due to the presence of error and error sources, okay, it is always possible to identify what is the source, what are the various sources of error, and to the extent to which these errors can be compensated, and also what type of error does each of these source induce in the system, and how, as I said earlier, how the effect of the error can be minimized. Okay, so if we try to categorize the type of errors, uh, we can have errors that arise during the measurement, and you can have errors that arise after the measurement is done, and that is when the transmission. So you, when you can have errors that happen because of the instrument being measured, or because of the person who is measuring, or because of some environmental factors. So, and these everything is happening, and the error is happening during the measurement, and the measurement signal is being transmitted for further usage. And you can also have errors occurring here. Okay, so when the errors are occurring during measurement, they can be systematic that are errors that are caused inherently by the system being measured, by the instrument being measured, and by other environmental factors. And you can have random errors also, okay, which are occurring due to random noise corrupting, or due to random biases that occur during the measurement. And the error can also be during the transmission, which are induced errors, which are basically the corruption of the measured signal. Okay, after this measurement, this signal can be corrupted due to induced errors, or due to the sources of induced errors. So let us look into each of them. So we had already we had a brief talk about the systematic and random errors during the start of the course. Okay, so what are systematic errors? If we refresh, systematic errors are associated with any particular instrument or the experimental technique. Okay, they are caused due to a faulty instrument, or an inaccurately or imprecisely understood measurement technique. Say, for example, if you have a ruler in which the markings are improper, they are not exactly done, then your measurement is going to be faulty, wrong, and that is an example of a systematic errors. Okay, and after, if you and these errors will cause a certain bias in the results, and this bias typically turn out to be in one particular direction. Okay, now if you see the diagram here, you have the figure A is a system where there are lots of measurements, lot of targets, shots are made, and all of them are around the bullseye, and they are distributed very close to this thing. So there is no systematic error in this case, neither there is random error. We'll talk about the random error a little later. So if you have a faulty gun, so you have a misaligned gun sight, then what is going to happen is all these targets are going to be shifted to one particular direction from this bullseye. So this variation is a systematic error. Okay. On the other hand, when you go for random errors, okay, you would see that these errors are unbiased. They are random in nature. Their bias is unpredictable. So now in this case, you see that various measurement have various errors of varying magnitude and varying direction. Okay, and so it even if you take 100 measurements, you really don't know what is the, you don't have any estimate as what is the amount of error or what is the direction in the of the error in the next measurement. In case of a systematic error, as you keep on taking measurements, okay, you will notice that you may notice that the errors tend to be in one particular direction. Okay, and so the way to combat the systematic error or the random errors is that for systematic errors, you need to recalibrate the instrument, and after recalibration, this bias can be corrected. Okay, say for example, if you know that if you have a spring balance which is going to indicate say 0.5 degrees or so 0.5 kg when there is no load, okay, so it's known that it has a systematic error of plus 0.5 kg. So if it is going to indicate, let us say 5 kg indicated, so then you can calibrate and you can say that when the indication was 5 kg, it actually corresponds to 4.5 kg because this is 0.5 kg error. Okay, and on the other hand, when you talk about random errors, typically even though individual errors are in random direction, overall the averaged out error is going to be 0. So which means that if you take a large number of measurements and average it out, then this random errors can be minimized. Okay, so in the case C, you have a case of random error. In the case of D, there is both systematic error and random error. So basically, systematic errors are going to reduce the accuracy of the system, okay, and random errors will reduce the precision of the system. Okay, and now going further, let us look at various sources of the systematic errors. Okay. So systematic errors can be can creep into system by various ways. One is by environmental disturbances or modifying inputs, as we say, that is when you have not understood. So there is a ill understood measurement circuit or the system. Okay, so you have not accounted for all the possible effects that can happen in that system, okay, when you're making the measurement. Okay, so that is one case. Okay, and the measurement itself, if the system is not calibrated properly or not designed properly, the act of measurement itself can cause a disturbance which will cause an error in the reading. Okay, so which means that if you are measuring a value, okay, if you had not measured, you will have a different value. It would have been a different value, and if you measure, you are ending up with a different value. Okay, that's a second source of systematic error. Okay, and of course, as the instrument ages, some of the parameters of the instrument change with time, and because of the wear and tear, and that will cause a change in the characteristics of the instrument. So maybe the gain may change, maybe some sort of a bias zero bias may change. Okay, that can cause some systematic errors also. Okay, and the unaccounted effect of connection, this is particularly significant when you have the instrument on one side and the control circuitry or the control room are physically separated by a large distance. So the connecting wires that go from this remote instrument to the control circuitry is going, if they are long, then that itself can cause some error in certain conditions. Okay, we'll look at each of these cases in a little more detail. Okay, first let us go to the environmental factors. Okay, so these sort of errors generally occur when either the instrument is working a bit out of its expected bounds, expected range, or the instrument has not been properly set for the biases. Okay, so for example, if let us say you have a ammeter and a little excess current is flowing through the ammeter. Okay, and because of that, what is happening is that shunt resistance is heated up and the shunt resistance changes. Okay, now since the shunt resistance changes, your ammeter resistance Ra to the RSH ratio is going to change. Okay, so basically the gain of the ammeter has changed, the gain of your ammeter circuitry is changing. So a different proportion of your input current I is going to the ammeter than when compared to what you had what it was originally calibrated in. Okay, that would make an error in the ammeter reading. Okay, so that becomes one source of error. And if you go for a mechanical example, then if you take a spring balance, and this is a binding screw of the spring balance which is usually used to adjust the zero. So if this binding screw has come a little loose or a little is a little too tight, and your zero is not, and then at no load it is not pointing at zero, that is going to cause some bias. Okay, so this systematic error from the environmental factor is going to make us a zero bias, as in the case of the spring balance, or a sensitivity change, as in the case of an ammeter, because its gain is changing, or in some other instrument it can cause both also. Okay, and since this effect is actually external to the measurement itself, because it is not arising from the act of measurement, it is completely within the instrument, that is the measuring instrument. Therefore it can't be easily separated out. You can't separate out the measurement from the error unless you calibrate it against a standard. So if I know that I have a weight that is exactly 5 kg, then I can put it on the spring balance, see the reading, and say what is the error, what is the systematic error here. Okay, or else in general it is difficult. So as an example, if you have a box that is of 100 gram, okay, and when you weigh it with or without something inside, and so there is the empty box is going to weigh 100 gram, and you keep the box on a weighing scale and it shows 1 kg. Okay, which would mean that either it is a very precise instrument and there is a 0.9 kg content, or there is some content, let us say there is a 500 gram content and there is a 400 gram bias, or else it can be an empty box and there is a 0.9 kg bias. Okay, so by just seeing this 1 kg and not really knowing the actual weight of the actual mass that is put in, you can't figure out whether at all the instrument has a environmental factor based error or not. Okay, moving on to so what I'm saying is that this error is difficult to separate out unless it is calibrated against standard values or standard measures. Okay, the next category of systematic error is the measurement disturbance. Okay, here in this case, what is happening is that the measurement act of measurement itself is going to cause an error. An example is that if you are going to try to measure the temperature of a small quantity of water with a thermometer with a large bulb. Okay, now, and let us say this thermometer is initially quite colder than the temperature of the water, and so the the water has to heat up this bulb of the thermometer. Okay, and that is going to reduce the amount of heat in this water, which again is going to reduce the temperature of the water. Okay, on the other hand, when if you have a voltmeter, if you are measuring a voltage across a particular resistance, okay, and you use a voltmeter, okay, and this voltmeter resistance is not very high, it will have a loading effect. Okay, and now you measure this voltage E across the voltmeter terminal. This voltage E, the measured voltage E, is not incorrect. Okay, it is the actual voltage across the voltmeter terminals. However, if this was not used, okay, if the voltmeter was actually not connected, or if the voltmeter was of infinite resistance, then the intention was to measure the voltage across these two terminals, but V may not be equal to E. Okay, notice in this case we wanted to measure V and we had connected a voltmeter. Okay, but when you measure the voltage from the voltmeter, the reading is E. Okay, this reading E was not incorrect for the circuit with the voltmeter. However, it is incorrect because it doesn't conform to what was the intended measurement or intended value of the voltage. Okay, and the way to combat this sort of a measurement error is to actually use more reliable instruments, or instruments that are more appropriate to the range. In this case, if you expect a resistance R here, your voltmeter resistance RV should be much greater than R. Okay, so I should choose a voltmeter whose resistance is much greater than this. And in case of the thermometer case, I should use a thermometer which is small enough, okay, such that the heat capacity of its bulb is not going to affect the overall temperature of the liquid whose temperature is being measured. Okay, the next type is the most common sort of, or most easily understood, that is the instrument wear and tear. So this, as the instrument ages, some of its components, say in a spring balance, the spring can become loose, or in the ammeter, also ammeter or voltmeter, the spring can become loose, the resistance values can be fatigued. Okay, in case of strain gauge, they can be plastic or permanent deformation of the strain gauge, and thus permanent change in the resistance, in the no load resistance of the strain gauges. Okay, and the obvious solution is an intermittent recalibration or repair of the instrument so that it can be brought back to proper use. Okay, the fourth type of error that can occur here are the errors due to the connecting leads, and this particular sort of error is significant when the measuring instrument and the control panel, okay, and the instrument are separated out physically by larger distances. Okay, so the connecting leads can have an effect here. Okay, so for example, if you have a 100 ohm RTD here, okay, and it is say 100 meter away, this wire that connects these two terminals, okay, can have a resistance R that can become comparable to the resistance of the RTD. Further, if this wire is subject to some temperature change, okay, that can cause error also. So there can be, instead of R, you can have R plus delta R also. So there is another factor of a temperature coming into this picture. So these sort of errors, so if R is comparable to RT, okay, there is an error. Now until I recalibrate or I take this into account, like we had taken in the 3-lead RTD or a 4-lead, in 4-lead RTD also, okay, like in the 3-lead RTD, we took into account that the RTD leads are long and the circuit was modified in a manner such that the resistance of the RTD leads do not really matter, okay. Or in other cases, you can use material whose resistance is not really significant when compared to the resistance or the property or the particular property of your measurement instrument, okay. On the other hand, let us say that so this was a case where you have an RTD. Let us say you have a thermistor, okay. If you have a thermistor here and you have long leads, okay, this thermistor resistance is much greater than the lead resistance, okay. So in this sort of a case, it doesn't really matter that the lead resistance is not a factor, okay. So depending upon the application, this can be a factor, okay. And so it should be taken into account if the application that you have has this problem or not. Next, coming to the point of eliminating these errors, or rather recapping it, by careful choice of the instrument design, you can reduce some of the effects of the environmental errors. That is, if the current sensitivity of the instrument, okay, not the current sensitivity, the temperature sensitivity of the instrument, okay, like in an ammeter, okay, you can use materials whose for the shunt resistance which are not temperature sensitive. So which means that RSH is not going to change so much with temperature, okay. And similarly this RA, therefore RSH by RA is going to remain constant, okay. So either choosing appropriate materials so that this error remains constant, that is one way, okay. Or the other way is that let us say in a voltmeter you can have the problem for a loading effect that you have in a voltmeter is that the voltmeter resistance is is comparable to the resistance of the circuit. Now, one easy way is that the voltmeter resistance can be increased a lot larger than the circuit resistance. Now, the side effect of this is that now the current that flows through the voltmeter, okay, is V by RV. That is the current flowing here. Okay. Now, if RV increases, this I is decreasing, which means that the sensitivity of the instrument is actually decreasing. Okay, so which in turn requires you to have the mechanical part of it, the springs and the mass of your assembly of the PMMC meter, that should become very light. So that is increasing the cost. So if you there is a cost versus accuracy trade-off when you are looking at the instrument design to reduce errors. Okay. Another more common way is the calibration to reduce errors. So a regular cycle of calibration and servicing can compensate for zero and sensitivity drift. Another way to compensate for a lot of environmental errors is the method of opposing inputs that we had repeatedly used in the strain gauge by using dummy strain gauges. Okay, so the dummy strain gauge is also affected by the same environment effect that the active strain gauge was subject to, and therefore the effect of these factors doesn't show in the final measurement. Okay, so the method of opposing inputs is also one way in which the systematic errors can be reduced. Another way is to use a high gain feedback. So basically this is used when you know that there are a lot of factors that affect your final reading. You are not really clear the range in which these factors can change. Okay, so Kc can go in a range, Ks can go in a range, but you are not really sure what is the exact value of Kc and what is the exact value of Ks. One way to do is use a high gain feedback, Ka. So Ka is much greater than 1, that is being shown. Okay, and however you have a feedback here where Kf is known exactly. Okay, now the measurement that you have is XO. So, and if you connect in a manner such that this amplified output is fed back by a negative feedback device Kf. So overall relationship between your EI, the input that is to be measured, and the output indication XO, okay, would be given by this expression. Okay, now since Ka, Kc, Ks is going to be much greater than 1, this one can literally be written as EI by Kf. Now what we have seen is that we are not sure about the exact value of Kc, Ks or Ka, but we knew that Ka was much greater than 1, and in consequentially this product is much greater than 1. Okay, and Kf is exactly known, which would mean that EI by Kf is exactly known, which means that from XO you can find EI correctly. However, there is a disadvantage. Nothing is free. The disadvantage is that we have Ka, okay, which is high, which is a high gain device. So we could have used it. So we have potential of cutting this off. Okay, we have a potential of using this circuit, okay, to get a reading that is very sensitive, okay, but it is error prone. Okay, if you remove this feedback. However, with the feedback you have a circuit that is exact, however it is not very sensitive, because 1 by Kf, okay, may be much less than Ka, Kc, Ks. This was the gain that you could have achieved, or this was the amount of sensitivity that you could have achieved if you had not used the feedback. This is the amount of sensitivity that you are achieving with feedback. The only problem is this is not exactly known, but this is exactly known. So you have to weigh the pros and cons and use this method if you want to do this. Another way to filter out or reduce systematic errors is the process of filtering. If we know the frequency of the error signal, that can be filtered out by using an appropriate filter. Say for example, if we know that the measurement cables are picking up radio power signals from the power cables, okay, so that can, and if I know the frequency of the supply, then that sort of frequency can be eliminated from the measured signal. Okay, and the errors due to this coupling or this pickup can be eliminated now. Okay, we can also have post facto correction of errors. Okay, like you can see this circuit. Okay, so if you know what is the Thevenin resistance RAB of this circuit, and if you know the meter resistance, and you have the actual measurement EM, and you actually wanted to find EO, you can use the post facto correction like this. Okay, so you can find EO by knowing that EM by EO is RM by RAB plus RM. Okay, on the other hand, let us say you have a strain not a strain gauge. If you have a resistance, okay, whose value at the ambient temperature has to be found out, and you know that it has a temperature coefficient of resistance rho of T. Okay, so you have a strain gauge. Okay, the resistances of the temperature of the strain gauge at T degree centigrade is found out, but you are interested in the resistance of strain gauge at 0 degree centigrade. Okay, so that can be backtracked by knowing the temperature coefficient of resistance of the strain gauge. Okay, so in this way, post facto correction can also be used. Okay, coming to the way the overall systematic errors is generally calculated, because we have seen that there are various sources of systematic errors and each source can contribute to some percentage in the error. Now, if there are 4 different sources, the maximum error is obviously the summation of all the errors. But in practice, this maximum point is never reached, because all errors are not expected to go to maximum or minimum simultaneously. So in general, it's more common to use the root sum square as the overall error. So if you have 4 different factors, x1, x2, x3, x4, then the overall error is plus or minus root of the summation of the squares of the errors. Okay. Coming that was systematic errors. Now, if you come to the random errors, as I said earlier, they don't have a particular direction of the errors. They are random. Okay, and they can be introduced in generally by the user. Okay, as parallax errors or interpolation errors during observation. Okay, and or due to electrical noise disturbances in the system. Okay, or some interaction, or due to random environmental changes. The main factor is that the random errors are truly random. Okay, they don't have any particular bias. If it turns out that any of these parallax or interpolation has a consistent bias, then it should be introduced, it should be considered as user induced systematic error and not as random error. Note that if there is a consistent bias, it's a systematic error and it's not a random error. It can be an induced error also, but it is definitely not a random error. Okay. And as I said earlier, the way to reduce the effect of random error is to take multiple measurements. Since infinite number of measurement is not possible, the effect of random errors can never be completely eliminated. They can be sort of minimized, okay, by getting better estimate of what is the amount of random error. And they say, for example, if you have a reading, say that says 10, by repeated measurements, you know that this reading is within plus or minus 1 from 10, okay, with 90% accuracy. Okay, if you had taken much more measurements, you can say it is between plus or minus say 1.2 with 99% accuracy. Okay, and the degree of this confidence, okay, of this measurement errors, the degree to which we can predict this depends upon the mean of the measured data and the degrees of freedom in the mean of the measurement data depends upon the variance and standard deviation of the data. So if you have a large amount of data, the variation and standard deviation of the data of the repeated measurement will give you an idea of what is the error bound that you can put in. Now coming to the third type of error, that is the induced error. Okay, the induced error is noise that is purely due to the measurement circuit, okay, and not the measuring instrument. So this is the after the measure after the instrument, the circuit after the instrument, how it interacts with external components and or within different components of this itself, an internal interaction can be cause of the induced measurement noise. Okay, and it is basically the measured signal that is coming out of here being corrupted post measurement, and this noise can either be a serial mode noise or a common mode noise. Now let us sort of better understand what this serial mode noise and common mode noise is. Okay, when you say serial mode noise, it or let me get it correctly. So basically, if you have two signals, okay, and means if you take the measurement signal at this end, okay, so you are taking this measurement M, okay, and this is the X, that is the actual thing that the instrument has measured. Okay, now if you due to some interaction with some external signal, if you have a noise that affects one of the channels, okay, so there can be noises, okay, let us say that it can happen that there is a ground here, okay, and let us say there is a mains cable going here that interacts with this signal cable and it causes some amount of noise signal, let us say N, coming into the circuit. Now what you are measuring is M, okay, but X was N plus M. Okay, so this noise signal has sort of corrupted your measurement now. Okay, so this is a serial mode noise. Okay, common mode noise is when you have a noise factor that affects both the channels. Okay, now when you have, so it's basically the serial mode noise, sort of serial mode noise affecting both the ends of your measuring terminal. So you have N1 here, you have N2 here. Okay, so the common mode noise is N1 minus N2 because that is what you are measuring here. Okay, so if N1 equal to N2, then there is no effective common mode noise, even though N1 and N2 exist, since since if they become common, then there is zero effect. Okay, like in this case, let us say you have the mains and earth that are getting capacitatively coupled with your measuring circuitry. Now if C1 is equal to C2, then the coupling effect due to this mains cable is the same across both the terminals here, both the lines here. Okay, so if they are equal, then it is going to have a zero effect. Going further, so the source of the induced noise can be inductive or capacitive. Okay. Usually, when you have a signal wire that goes close to some power cables, and the signal wire is transmitting high frequency signals, radio frequency signals. So because of the high frequency component of it, there can be an inductive coupling that happens between the mains cable and the power cable and the signal wire. Okay, and that can cause some inductive coupling. Okay, and similarly, when you have high voltage lines that are really close to your signal measuring circuitry, you can have capacitive coupling occurring. And as I said earlier, this capacitive coupling taken piecewise is our sources of uh, series mode noise. However, if the coupling is the same at both ends of your measuring instrument, then it is going to, like C1 equal to C2 or C and 3 equal to C4, then it is going to cause uh, no, it is going, it is not going to cause any effective common mode signal. Okay, hence there is no effect. However, this is not really a case always. C1 may not be equal to C2 and C3 may not be equal to C4 because these cables may not be really parallel with the mains cable and the earth. Okay, so effectively there is some series mode error that can occur. Uh, Going further, other sources of noise are noises due to multiple earths. This is because typically your measurement circuitry is supposed to be isolated from the external power circuitry. Okay. However, that is in practice, this really doesn't happen. Okay. There is always you tend to have earths in your measurement circuitry and earth in your power circuitry, and typically if these two earths are at the same potential, let us say E1 is the same as E2, then there should be no problem. Okay. However, what can happen is that E1 is far away from E2 and there is some potential difference between the point E1, which is the power circuitry's earth, or the measurement circuitry's earth, which means E1 equal to not equal to E2, and which causes some spurious current flowing through this entire measurement circuitry. That is going to cause some noise error again. Okay, so there will be leakage current paths, and this leakage current path is not a problem if both the earth potential is the same as both at the sensor measurement and the power. Okay, however, if it is different, that is going to cause some problems. Okay. In addition, in this circuitry, and another point is that if you have a situation where your sensors are being powered from the same electrical supply that powers large large machinery, whenever that machinery is going to start or stop, there may be a power spike or a voltage spike in your measurement circuit. Okay, and that is going to cause some spike in your readings also, which actually don't exist. Okay, and this, as the name implies, the spike are of short duration and large magnitude now. Yeah. Going further, these are sources of small spurious potentials. Like in a thermocouple, you can have thermoelectric potential, that spurious thermoelectric potential caused due to unintentional thermocouples being formed at different leads. Okay. In electronic circuitry, you can have random variations coming up as short noise due to random variation in charge carrier transfer rate across the junction. This particularly is observed in low current transistor circuitry. Okay. And in certain circuits, due to improperly soldered joint, you can have small batteries being formed there, and that causes electrochemical reaction, and that causes some spurious electrochemical potential is induced. And like the remedy for other types of noises, you can also remedy induced noise also. The simplest way to combat the inductive and capacitive coupling is to braid wires. So the wires, the two signal carrying wires are physically close together, which would mean that any serial mode error that is going to affect both these wires A and B equally. So the in effect, at the at the measurement instruments end, there is not going to be any error that is caused due to the coupling. So that can be minimized in that sense. Okay. The way that the earth problem can be reduced, or the multiple earth problems can be reduced, is by uh, isolating all of them separately. Okay. So you can have one earth for all the power circuits. Okay. And you can have one earth for all the logical circuits. You can have one earth for all the analog signal circuit, like the measurement circuitry, and all the metallic parts of your instrument, of the equipment, can be connected to a safety earth, and these four earth terminals can be isolated from one another. Okay. And since they are isolated, the leakage current path no longer exists. Another very common way to shield to reduce the induced noise is to use shielding. Okay. In this case, what is happening is that all the signal wires, of course, they are twisted pairs. They are put in a shielded jacket. Okay. And so there is an outer metallic jacket, and there is a drain wire connected to this metallic sheath. And so any coupling, let us say there is a power cable here. The power cable is coupled, it tries to couple with the circuit here, with the wires here, but since this drain wire is connected to the ground, it couples very much more easily with the sheath. Okay. Or than with the signal wire. So this path along the sheath is going to give you a much more easier path for the coupled, for the inductive or the capacitive coupling circuit. Okay. Rather than the actual signal wires. So in effect, the signal wires are sort of protected from the effect of any of this inductive or capacitive coupling. Okay, so with that we come to this end of this lecture. So these are the references. You can see chapter 21 from Nakra and Chaudhary from the book Instrumentation, Measurement, Analysis, and chapter 3 on measurement uncertainty from Alan Morris and Reza Lengari. Okay, thank you for your time.